Hello, and thanks for joining me for this talk. So what I will present today is joint work with Ivan Di Liberti, and who is also a member of Ithaca. And the title of my talk today will be Context, Judgment, and Deduction. So I want to start with you by looking at these two rules. They come from very different deductive systems. On the left, we have dependent typing or type dependency or whatever. And this is, of course, a rule that you can find in type theory. And on the right, you can see the cut rule. And that is the cut rule from whatever deductive proof theory system you wish to choose. So natural deduction, in this case, or Gansen calculus or whatever. And first of all, I want to notice with you that there are some similarities happening here. So there is a context part that is, let's say, permanent throughout the deduction, and that is what I marked in blue. And then there's a red part, which is the part that we want to get to, which I marked, as I said, in red. And then there is a middle part here, marked in yellow, which does something kind of like a bridge, so that we can take two judgments and get to a different judgment of a certain kind. And on the left, the yellow part sticks after the deduction is completed, let's say. On the right, it just disappears. But there are some parts about this that sound familiar from one side to the other. On the other hand, they're very different in the sense that, for example, on the left, you have judgments of two different, let's say, kinds. Meaning that, for example, the first judgment that we see here is a judgment about terms, while the second is a judgment about types. And instead, on the right, you only have judgments about formulas. So there are some similarities, but also not every other judgment is the same as any other. So there is some differences with this regard. So what I will try to answer today is, why does this happen? And also, how do rules really work? And I only mean this by a syntactic point of view, but how do these judgments combine to get a new rule? Why these rules? And also, since in common deduction systems, the way you put in constructors and connectives is just by adding new possible rules regulating how the constructor or the connective acts. A question about rules is a question about constructors and connectives. So we'll try to answer some of this during this talk. So first, reasonable answer is proposition as types, and any logician will probably say something of this kind. And actually, it does explain some similarities because this paradigm is very strong and it has a very rich history. So some similarities are explained by this, but it doesn't really capture why these two rules are so similar in the shape, and what does this shape mean? Also, how come some judgments have different kinds? For example, there's some judgments about terms and types, and they predicate to very different things. So there is a very famous article from Philip Walder, and I think the title is precisely proposition as types. And there's some evidence of correspondence with William Howard, and he said, we have constructions acting on constructions. And the reminder today will actually be, we'll have functors acting on functors. So what I mean by this is that I will try to convince you that these two different judgments will be coded into just one category, and that will be a fiber category. And this consequence will be, again, a category, and there will be a functor between these two categories. So functors acting on functors. So in order to give such an explanation, we need to give an account of context, judgment, and deduction, like progressively, say, complex definition. So this will be what our definition of pre-judgmental theory entails, we say a pre-judgmental theory is specified through the following. So a category, context, collecting context and substitutions, and usually we'll ask of this category to have a terminal object so that we can compute the empty context. Then a class of functors into context, and we'll call these judgment classifiers. And you see what I mean by this in a few slides. Then to compute deduction, or to describe deduction, we'll have rules, meaning a class of functors between domain of things appearing in the judgment classifiers, say part of the definition, and cuts. So a class of two-dimensional cells filling some triangles induced by rules and by judgments. And I know it's a lot to say, but to ask, but just forget this part for a moment. I'll try to convince you that you don't need this. But we just mean that if we have some bound between two judgment classifiers, we might want to say that there is some relation between what happens here and what happens through this path. So this is what the C class does. And the name cut, we've been told, is a bit confusing. So if you have better name for it after the talk, just write me an email, please. Okay, so as I said, we just focus on the first three elements. So, and I'll try to explain in which way we interpret this to be a syntactical object. So whenever we have an object F over a context gamma, we will read that in context gamma, big F is, let's say, declaring F. So with respect to gamma, big F is declaring F, or in context gamma, big F says F. And whenever we have F and F prime over the same gamma, and they're equal, say with respect to the category they're say observed in, we read that in context gamma, F and F prime are equal with respect to F. Okay, what does this mean for this theory? It means that if we follow this rule, we start from something in context gamma, which is some F, and then we apply lambda. What we get is some lambda F in context G lambda F. And the first thing is, let's say, witnessed by big F, and the second thing is witnessed by big G. And these will read as a rule. What about the cut? The cut is just saying what I mentioned, that maybe you wish to put some condition between the two. And this, in this case, we will only consider, let's say, contravariant conditions. So a natural transformation going from, let's say, the consequence to the premise of the rule. Okay, so how do we interpret this? I want to look at a simple example with you, and that is what we called toy Martin-Love type theory. So consider a category of context as substitution, whatever you need, what your favorite category of context and substitution for a type theory, and then two functors u and u dot. As a rule, consider sigma, and of it ask that it commutes in such a way, and this is witnessed by identity in C. And we think of sigma as kind of a projections, meaning that in u dot we collect pairs, terms, and type, which we just put every term together with its type, so that we can allow the same term to be of being two different types. Okay, well, how do we read this? In this, how do we read an object here? We say that in context gamma, small a, big A, according to u dot. And we, of course, read this as small a is a term of type big A in context gamma. And clearly, same goes for the second, meaning that in context gamma, big A, according to u, is a type in context gamma. And what about this rule? This rule is just saying that if in context gamma, small a is of type big A, then in context gamma, A is a type, or the type of A in context gamma is a type in context gamma. And I want to stress the identity part, which bounds in a way the connection between the context of the premise together with the context of the consequence. So here the identity is stressed by this cut. And this is all fine, but we can't do anything with it. Meaning we only described a few trivial rules. So how do we compute more? And the interesting part of this theory is that we can express computational power of a deductive system into two categorical constructions. And this is what brings me to the second definition of the day. So I will say that a judgmental theory is a pre-judgmental theory such that R and C are closed under composition. As you wish, you might want to compose rules, and same goes as coherence data that is contained in cuts. The judgments are precisely those rules whose codomain is in context, meaning that judgments are just some very, very, very basic rules, and whatever you find in rules, you can just bring back to context and then derive a judgment of it. And that R and C are closed under finite limits, sharp lifting, whiskering, and pasting. And by this, I mean that some two categorical constructions are closed through this operation. So finite limits will ask of pullbacks, for example, meaning that if we have two judgments, then we can pull back and get again a judgment. Also, that universal arrows concerning this limit are again in R or C respectively. Same goes for equalizers. Sharp lifting is what we called the operation of lifting a two-dimensional cell along a fibration, because as I promised, a lot of these will be fibration not only functors. And we haven't found any reference for this in the literature. So if you know something like this, please point it to us. And then just whiskering and pasting, meaning some standard two categorical operations. So these will express the, let's say, computational power of the deductive system. So I just want to have a look at pullbacks. And my claim is that they are perfect for coding nested judgments, such as the premises of the two rules that we started from. What I mean by that is that if we have a judgment classifier F and a judgment classifier G, and then we have a rule lambda between H and G, then when we compute this pullback, which I write with this weird dot notation, which is just a simple way of writing things in when you have to compute pullbacks, and it's very useful when you try to read these diagrams. Then when we look into an object here in context gamma, because this is all commutative, so they are all over some context gamma here, what we really mean is that there is an H here above some gamma here, and an F here above G lambda H. And if you really look at it, squeeze it a bit, you can see that this is starting to look like the connection that we wish we had to compute, let's say, different premises. Because of course, if we had two judgments not related in any way, that they wouldn't be useful to combine together. And this is what actually pullbacks do. They compute nesting judgments, which are those that we call this way. Okay, so I'll try to show you how these two categorical constructions actually, what can we do with this? So I can take the Toy-Martin-Löw theory that we started with, and in the judgmental theory generated by this quadruple, we found the following, for example. So we can consider the diagonal, and then we can take the equalizers of the two projection, and then there is a unique arrow from U dot into the equalizer. This is just category theory, basic category theory. But if we read this as a rule, we find that from some small a in context gamma, meaning some small a of kind U dot, we find something in the equalizer of the two projection. And I'll ask you to have a pause on it. And I'll show you another example and explain what this means. Again, if you this time take the equalizers of the projections along the, say, the type part, These are isomorphic, of course, and then we have this projection. So we have this community triangle in particular. We take this isomorphism, and these reads as such. So we have some small a coming from this part, and some pair a, b, which are equal according to the projection, and these are contained here. And then we apply this construction and end up into u dot. And this is another rule, but if we really break it up, what these two rules mean, well, in the first case, it means that if we take a term of type A, then A is equal to A according to A in the standard, say, type theory sense. On the other hand, the second we can read as, okay, we have a small a here and a pair A, B, which are equal according to U, then we can get to some small a, which is instead of type B. Why is it of type B? Because it goes this way. Okay, so we can express something this way, but I want to show you that this is actually enough to say a whole lot of deal things. So we expand our Toy-Martin-Love type theory as such. So we again take the category of context and substitutions. We ask of U and U dot to be fibrations. Then we extend the rules with the delta right adjoint to sigma, and these will perform context extensions. And then we just add to cuts epsilon and eta, the co-unit and unit of the adjunction, and we ask of them to be Cartesian. So what I mean by delta computing context extension, I mean that if you read this rule, it starts from an A of kind U in context gamma, and it goes through this path into this. And actually, if you break it up a bit, you'll see that what it means is that you have a type in context gamma, and you get context gamma just A, a special term in the extended type, so that it makes it to the context extended context. Okay, how do we use this? So first of all, we proved that if U and U dot are discrete fibrations, then the judgmental theory generated by such a choice is equivalent to a natural model allowed. And if you read about natural models, you know that this means that it's also equivalent to categories with families, categories with attributes, and special kind of display maps, display map category, of course. So these, in a certain very, let's say, thin sense, works just as well as some standard categorical models do. But not only that, we proved that judgmental theory generated by these choices contains codes for all rules of defended type theory, meaning that this is also enough. So we don't need the discrete part. We having fibrations is enough to code all the rules that one wishes to have in dependent type theory, of course, without constructors, but we'll get there to that in a second. And I want to show you a bit of how this is done. So one maybe one of the hardest part of coding dependent types is that of dependent families. So coding pairs as the four that I wrote here. And the way we do, as I mentioned, is pullback. So if you read down here, we have a term of type A, then it goes through sigma into its type, then through delta its extended type via terms, and then we just forget everything and just get to this context, so gamma dot A. And we read here, so let's say, for example, start here. So we have small a here, and here we have a type, and this type has the same context as this, let's say, path for small a. So you can see that these actually map precisely this nested judgment. And this is actually very easy to do. We just compute pullbacks. And this is also, not only it's easy and versatile, but it's very interesting and say suited for coding more complex rules and judgments. So as I said, we ask that our system is close to sharp lifting, meaning that we can lift two commutative diagrams along the fibrations. So we do it twice, and we do it like this. And so we start from here, and you follow this path, you get to gamma. And you go through this path, you get to gamma.a. What you do when you go up here, you start from pairs small a, big B. You see that this u dot reads small a, and this u reads b, such that they're in the relation, let's say, stated by sigma delta. And going through this, you get to something of kind u. Not only that, but this something of kind u is related to the b we started from through some map. And the same goes for the upper level. So if you have small a, small b, you go up here and then project, and you get something of kind u. And this something is related to b in such a sense. But what does it mean to have something doing this job? This is exactly what we call dependent typing and dependent types and dependent terms. So, and you see that this type agrees with this type through this sigma typing factor here. So, two categorical constructions, coding rules. Not only that, but we can use this to also describe constructors, because as I mentioned, constructors are only defined by the rules that you describe them in. So we prove this, that judgmental dependent type theory has p types if it has two additional rules, p and lambda, such that the diagram below is commutative and the upper square is a pool. And I read this with you for a second. So here we have something coming from u dot delta u. That is, we start from gamma dot, a in context gamma and b in context gamma dot a. And what we get is something of kind u, meaning a new type. And these commutes, meaning that they're all in context gamma. And same goes for the upper part. So we have a type and a term. And they're in the relation described like here. So what we do is getting something of kind u dot. And the typing agrees because all of these commutes. And these are just introduction and formation for the type constructor. The elimination part comes from the unique map induced by the pullback from the classifier. So you just need to know that when this is a pullback, actually a weak pullback, there's a unique map going here that does what we wish to do. And this is the elimination rule, and eta and beta computation are the two related isomorphisms. It's also very interesting because it tells you that you can, if you, for example, don't agree with the choice of beta computation, this is where the point where you just ask less of the theory. For example, you just ask that it's a weak pullback, or there is only just a section or a traction, and this is actually the point where you would do it. This not only works for dependent products, but it also works for all basic constructors in marketing love type theory. For example, identity types also fit this pattern in the same precise way, and dependent sums just fit into this presentation. Not only that, but actually the computation that one does are always the same. So you see that there's a unique map, and that will be elimination, and then we have eta and beta computation, and this is introduction, this is formation. So actually, if one computes the deductions, or say we can extend the notion of type constructor by saying that a type constructor is whatever fits reasonably as an arrow on the left of a diagram, such that the commutative and as a pullback. So that is very interesting, in my opinion. But I want just to conclude with you where we are at. So we describe a general theory of judgment using two categorical means and prove its coherence with respect to dependent type theory. And with this, as I showed you, we get a definition of type constructor. But we also applied it to natural deduction calculus and to some flavor of internal logic of tokens. And so this is what we have done. I already showed you briefly the first part, of course, but you can kind of guess how the rest works. It's just diagrams. There's a lot to do, actually, but I believe, for example, we proved some coherence results, meaning that we can code into the judgmental theory whatever rules one wishes to have into the deductive system I mentioned, but we don't have a completeness result, sorry, meaning that we wish we knew that whatever diagram we write had a correspondent, let's say, deduction, so that it makes sense. That we don't have. We're working on it. The second thing that we should be very interested to look into is to extend the theory in order to, let's say, capture more type constructors and more connectives. Well, actually, that is very, very bleak. But more type constructors, for example, inductive and co-inductive type constructors do not fit the pattern that I showed you before. But I personally believe that would be possible with some limits and co-limits, but not sure about that. So that would be very interesting to do. Also, monads would be interesting in this context because every monad comes equipped with something that we now call rules and cuts. And so every monad is saying something of a rule. And of course, computer scientists know this. And we believe that this can be studied as modalities in this context. So that would be very exciting. And then another thing that would be quite interesting, in my opinion, is to try to express expectology connected with the point that I mentioned earlier, to express new logic. So modal logic, linear logic, and if you have any ideas about this, just write me. All right, so thank you for listening, and if you have any questions, just please write. Bye.